Yeah, welcome everyone back to high performance computing, to our lecture 8 on debugging, profiling, and performance analysis. In the first part of the lecture, we learned the origins of debugging. We learned why that's so important. I want to have a correct program in the end that really works, makes sense. And then we went one step ahead and said, actually, we don't want to do this manual with printf statements. There should be some tools that actually help us. And with the video of Total View, you have seen one tool, but you can really have, of course, also simpler debuggers, DDD, GDB debuggers, and so on. But immediately also, it's clear that serial debugging of serial programs is a difference than parallel debugging. And this is also where then tools like Total View strike very much, as immediately if you have lots of different parallel activities. On top of this, the requirement of tools, we also learned that essentially to really understand what's going on, what's happening in a program, profiling is needed. So in a way, a kind of aggregation of statistics where I could use, for instance, the MPI profiling interface as an example where it's shown that you can count the function calls, let's say MPI send, for example, and how many times this was actually executed. And essentially, this is now the key ingredient to something we call performance analysis tools, where we can perform actually optimization methods to the code, where we will identify patterns of wrong, let's say communication behavior, for example, and how we can correct this. But before we do this, of course, we have to have a yardstick. And this yardstick is basically used with essentially typical profiling of an application. You would have a trace, so to speak, of this parallel application. And these are all terms which we will also come back to now in the second part of the lecture to make this a bit more clear, what we now mean with replaying, what we mean with tracing, and so forth. So in a way, we really are at the third part now when we think about performance analysis. And this is really building on the elements before, particularly the profiling, when we basically, of course, should only do this also when you have done all of this already in debugging, right? So this means the program should essentially be correct and don't intertwine this by doing performance optimization. Then now performance optimization, as the name suggests, is really tuning then the program for a better performance, better speedups, and so on. The idea is, for instance, finding with several dedicated tools like Scalable, then some interesting slow execution, so waiting times maybe, where some processes are idle and we don't know why. We want to understand why, and sometimes this is also actually identifiable as certain patterns. So it's the own, let's say, fraction of parallel programming of HPC community as such. You would say there's a performance analysis community within the HPC community that offers certain tools, that gives workshops, tutorials that are really experts in that area. And you see also when you think about a proper HPC system software environment that you would essentially want to have in a HPC center today or in a basically university cluster, you need an operating system that's clear, scheduling as we discussed for multi-user, and also monitoring a little bit. But you definitively for code tuning should also consider performance analysis tools like Mpi, like Scalable. They have all their unique selling propositions. So of course, it depends of how much effort you really put in to make them all available essentially at certain centers. But of course, it might sense to even combine them today. And we see that some of them are even interoperable these days. So it's really a key field in HPC, as we said earlier a little bit, but now we really want to understand it a bit more in detail when we really think about how we can now measure and analyze runtime behavior. In particular, as we said, also essentially on a parallel program, right? So parallel program, which calls MPI wait all, for instance, somewhere we want to also understand what type of performance problem it would be. Right? What is a performance bottleneck? Maybe that's a common pattern. And here and there you have really this GUI, which helps you. Is it somewhere specific in the system? So has it maybe relevance to I/O? A lot of elements where we really need to go through. It is a really dry lecture, so I go through this a little bit quicker. Also because we will have a video afterwards where basically the idea of Scalable is shown. And then you get, of course, much more the insights, how this Scalable is really working. Here it's a little bit the kind of metrics tour, as the experts call it, where you can think about what are the measurement metrics where we now would think about doing the yardstick versus the improved, performance. You would have generic measurement metrics, which is of course a time, which is a CPU allocation time, including the execution time, but also then of course the overhead that you always have to have when you basically measure something, because you put in just something for the measurement or for the output. An example would be, let's say, the printf statement that just puts a variable out is an overhead, because usually it would be not printed out. So in the end, this is a very tiny example. But if you think about, you do this, let's say 250,000 times with 250,000 processes running on a highly scalable HPC machine, the overhead gets bigger. Of course, then using the profiling interface, this measurement gets even more higher when you want to have every MPI application that you run across all the different processes, and every MPI function it's calling essentially then also profiled. So this is another overhead of measuring. You have the visits to really understand how often a certain function was then executed. You have hardware counters you can use for each function. So different ways how you can actually use this inside some performance optimization tool set. So for parallel programs using MPI, particularly, you have the following elements essentially. When you have the overhead a bit excluded here, but you have the overall time, which means the execution of your program, and then you dive into MPI. The MPI again can have different statements. As you remember, we have communication with collectives like MPI broadcast, point-to-point with MPI send receive, but we have also learned about barriers, synchronizations, which are actually collective operations, which is something also to measure. And the MPI IO, if you remember, for having data addressed, is also, of course, which actually contributes to the overall execution time of your MPI application, including then, of course, the overhead more or less here of init and exit of the MPI as well. That is also something to measure. Now for OpenMP, that looks a little bit different. Still, the principal idea is similar. We have time, right? And we have a bit the overhead now neglecting of the measurement, but we have idle threads that we can measure, which are actually not really used in the execution. It's already a big indicator of something maybe can be improved. And then execution time, which is of course now not MPI, that's what we have already, but think about this hybrid programming. I have, of course, the whole tree of MPI here as well, right? But when we go to the OpenMP, we have synchronization methods, as you remember. We have this fork ID of actually having new threads, and then also a flush and so on. Flush is basically then also time spent in OpenMP. Flush directives we didn't really cover it in our lecture 6, but don't worry about this. It's just an example of a certain set of tool sets. Now, how would this be measured? So we have a need for automation. I can assure you, with having large-scale HPC systems and then larger HPC applications, you don't want to do this manually or kind of visually tracing it yourself. This kind of tools is a really necessity, and they are doing this automatic tracing analysis process. You essentially have there also the opportunity to automatically search for patterns, right, of inefficient behavior. This is much more quicker than anyone from us manually could do it, or just by looking at some visual trace analysis manually. And you can, of course, employ it also really large scale, right? So in large scale HPC applications. And it covers the entire trace. It's also good, not the human that maybe overlooked something. And then you really have the opportunity to classify some of the behavior in an automated fashion, or quantify so the significance with it. So when you want to have this process a little bit explained, you would have a low-level event trace, what's happening in your application. You do an analysis on it and have a report which has some results. And then it really shows you that in the certain call paths within your specific API application, you have certain properties and locations which you can identify. So it collects a lot of information about the program for post-analysis. So of course, we want to analyze the performance of this application afterwards, right? So after we have done essentially the run, And that's what we call a post-analysis. And this is done then on top of all the profile aggregated statistics that behavior was basically done in this tracing step. So hence, we need several steps to do this. A tracing technique, to really understand it in general from the functionality, you would have your normal program source code in MPI, basically, and C maybe, and you have your compiler, and you know that you basically that then get an executable, which is your typical application plus the MPI library you maybe use for different, let's say, MPI communication exchanges. So this would be kind of step 0. Of course, you would start always with your own program. Now, in order to augment now the tracer and the idea of tracing, we have to add something to this. So firstly, we have a so-called instrumenter that actually has automatic code instrumentation to put this close to the compiler. And basically then automatically processed is then this kind of program, which is now an instrumented executable, right? Having from the instrumenter already everything inside, where also now the measurement is taken, where the measurement library is already added to this. And of course, you can amend it. This instrument is then using really the standard profiling interface, PMPI, to really, for instance, measure how often certain MPI events or functions are called. Now, when you want the kind of runtime summarization analysis, of course, you can have there's different configurations usually to which extent you really want to analyze it. But usually this application will run, it will drop a summary analysis at the end, and then you essentially look in an analysis report examiner for some certain flaws in the program, right? And this, of course, is a loaded program here. It could be a very good tool that identifies very problems here, which we also will realize in a certain moment. Now, for the second part B, we see here then really essentially what's happening is that we have part of this measurement lib, then also the trace coming out. So the trace means really now that I have this parallel trace of all the different elements which are taken, right? So it's not just the summary statistics that we learned with the profiling interface and so on. Here we have really time-stepped events that actually for each thread and so on really dropped down and essentially kept for replay. So you have a whole execution, so to speak, of the parallel application dropped that you also in the trace then actually can reuse, can reanalyze also with a specific tool in question. So you have kind of two ways how you now basically will look at this, right? When you think about tracing, you have on the one hand, then this automatic code instrumenter that's really needed to do this in an automatic fashion to perform basically runtime measurements, event tracing using MPI profiling interfaces. So the tracing then really requires a specific measurement library because essentially the normal MPI techniques for this are quite limited. So that's why you have several specific libraries to enable this, as that we will also see later on. And then this trace architecture enables really serial and parallel event traces. And then you can really conveniently analyze it with a powerful analysis report tool that is really examining or looking and checking what is the parallel performance problems, what are the execution performance properties and metrics, and can we find certain patterns where we maybe have a problem in the application. Of course, this tracing technique has now one drawback if you think about it. Of course, we do a lot of analysis already. We kind of, with this tracing, you do a footprint if you want, right? A little bit of this application. And you can see if you have a typical uninstrumented execution of your MPI application, it scales quite well. Here's the wall time. Essentially here you see the scaling behavior as well. But when you have the trace analysis, including IO, now you basically see also, of course, that this is now complete different runtime, right? It has an impact on the runtime and the scalability of codes because you write now much more events essentially out. All the timestamps, when you were entering an MPI operation, when you were coming out, when you were entering a function from yourself, when you're coming out. So essentially, this is already an overhead, basically, or basically the drawback of doing tracing. And of course, then also think about that in order to run such a parallel computed application trace, right? Again, if you want to really run it then in a replay, of course, you need also parallel trace replay, right? You cannot just do it now on one processor. That would be quickly running out of memory or so. So essentially the replay and analysis of these original parallel codes requires, of course, parallel tools also, right? And this is an important part. You cannot just attach now some DDD to it or GDB to it. So these techniques needs to be scalable in itself. I think that's the key message I wanted to leave in the table for you. And then when you think about the formats, a very good way of working these days is that people move towards so-called open trace formats, where in the past people have always used their own, let's say, different types of trace formats. Here you see the different codes that have been used before, or tools, Epilogue, which is, Kojak Scalaska predecessor, then Parallel format, the STF, Tau was a very important one, the Paraware format. So all of them had their own ways of how you basically now drop all of this tracings and the performance analysis, and different open trace formats available. Of course, it's still work in progress, but it's coming already quite far these days with having a unified system also across the different performance analysis tools. So what are these performance analysis tools? And you will see again a little bit those we have already listed above. One example was, of course, Valgrind, again, profile memory usage, but with this you can also have performance analysis done. You have Mpi, which is also trace-based and offers, this good timeline view that we have seen in one of the image before. Scalaska is basically something which then on top of all of this gives you a nice GUI, but also identifies certain common patterns we will talk about very soon. And there are different other ones like Periscope that have, several automatic performance analysis capabilities, and essentially some other elements that are more related to hardware performance counters, or basically then a SCORP system, which is more or less be considered by an infrastructure for measuring performance, which essentially can now be used by many other tools as well. Of course, in this domain, you have also commercial tools for performance analysis. You would go for the VTune here, amplifier tool as one example, or SGI ProPack. There are different ones over time. They keep changing, of course, here and there as well. But the commercial tools have, of course, the advantage that they are often more powerful. But of course, the disadvantage with those tools is that they just simply cost, or are just available essentially when you, let's say, have some NVIDIA or let's say certain elements in your stack. So let us look a little bit on the Scalaska toolset example. So the idea that you just had here with the general principle was a bit derived from the way exactly how Scalaska works. This tool is available as open source. Everybody can use it. We have it here installed in Iceland as well on one of our clusters. And it's really using the tracing techniques and has kind of 3 tools, which is part of the Scalaska distribution. And they reflect essentially the run through this application. And this would be important also maybe to know for the exam. So compiler instrumenter that we have above here, there we have the so-called Scalaska skin that automatically helps you to instrument then the executables. Then we need someone who is really collecting all the measurements and analyzing. That is this Scalaska Scan TB, which then gives you essentially the idea of how you basically drop all of these aggregated statistics, the measurements. But of course, what you also want to have is then the lowest part here. You need some powerful tool, what you have already seen in here and there on some of the slides very early on in the lecture, which is the Scalaska Cube tool that you have seen, really an analyze, report, examiner in the GUI-like fashion that you see here. So again, it really shows you essentially what type of problem is actually faced. Maybe let's say here a late sender, and we come to the definition of those very quickly. Then basically you see where is it happening, right? So where in my source code is it happening, what I have here, in particular when you focus on MPI statements like MPI wait all, and then the topology of network of communication, where in the system is now the problem, how is the call patterns. And the interesting thing is now that with this open trace format I was alluding to, and also with the SCORP infrastructure for measuring you will see that all of these systems in a way can really be used together. And many systems already also give you the opportunity to have all of these elements together installed. And this is the beauty of, let's say, ScoreP, which really then builds on top the normal MPI, OpenMP, or hybrid applications that you already know. But then based on this infrastructure on ScoreP and using and leveraging then this open trace formats and code profiles, which are, let's say, a little bit different than these event traces, you can actually inform different tools. You can visualize the event traces in Mpi. You can have this large scale analysis in Scalable to really detect maybe of waiting states and so-called patterns that we will review now. And then Tau is basically also interesting with a performance database and another type of tool to look at the universal performance. And Periscope is also here used every now and then for performance properties and the identification and so on. So in a way, you see quite a substantial set of tools, and we are all not directly experts in that, but there are experts in the field that then offer, let's say, 3 days Mpi, 3 days Scalable, and then you really get also quickly in the way how to use these systems in practice with your applications. Now, optimization then, when you use these tools, could be in different areas. So one, of course, would be identification of, let's say, more general aspects that we have here. So these are very common ideas of optimizing, for instance, the memory access, where you have essentially the setup of R and N, and the overall execution time really depends on how you essentially have your inner and outer loops essentially defined. So one example of this would be against, for instance, also here, when you have the switch of indices that you essentially, or that are pulled here, right, where J is going over to some dimension and E is going over to some dimension. But if you put it like that, that basically the inner loop here actually is the outer part of this array, then you would have, let's say, a very unfortunate memory access paradigm. But if you change it just this kind of indices, this is a whole different way of the memory access paradigm. It is, of course, reflecting of the way how this computer is accessing the memory. But in this way, it would be taking the outer loop basically later and always taking the inner loop here. And with this, it's, of course, much quicker because with, you know, being consecutive in the memory and so forth. So it really depends, of course, on the application problem, but it shows one of the most easiest examples of how you can do very quick changes to the source code by optimizing orders of magnitudes your source code. But this is a very general technique, not directly for parallel computing. It's more memory access, but you can imagine if you do this in parallel on many different CPUs, this is, of course, then also a big gain. Now, when you think about now as a couple of other examples, going more now in examples for Scalable, you would see that you basically have here a call tree or kind of trace already, where we know in some of our data science problems, we go in and then we can look where are here basically the problems. And here's weighted barrier, sometimes a problem, or a late broadcast. That means I use a lot of broadcast apparently here, which is interesting. So let's look into this. And once you go into this and you look, okay, there's lots of time spent in broadcast. Let's look at this as well. So, and if you go to the source code, then of course, as an example, you see incredibly often is broadcast use. And why? Because it's often basically just put in a for loop to all the other processors, right? To send data to all the other processors, and of course, including yourself. So, but what we know already is that essentially this is not really necessary, right? We have learned there is already an MPI altogether that can do actually the same collective operation again, but, you know, is basically then avoiding that you have to have another loop on top. So that means it still gathers the data to all the processors, but there is no point of doing a for loop around it. So you can have just one statement, MPI altogether. And this altogether is incredibly good implemented so that you really can, you know, much better scale your application. But you see also here in our runs that we had, here's the paper for this, where we had run into memory access problems, right? Already with 64 CPUs. At that time, with the support vector machine and data science, you cannot come very far. So essentially, you see there's not anything we can do there. And it doesn't matter how you basically show it here in the time of kind of speed up or essentially in the times. But the key point is that with the optimization to MPI all gather and then with others, and here you see a difference from, then collecting this with all reduce, a kind of counterpart, we came up to scaling again. So we could get higher. Let's say, for instance, use 128 CPUs. This was used by just using Scalaska and then, of course, looking through the source code and find very, let's say, beginner errors, if you want, of how you MPI program. Of course, it is naturally to use broadcast. It's very simple, but when they're optimized programs for this, it's very important to think about these ways as well. So in a way, you see, instead of, it's a kind of general pattern I can now basically recommend to you, right? That you really have to get into your mind. Instead of multiple times call broadcast, that now you can use the MPI all gather instead of it to really distribute what you essentially there have. You don't have to put another loop to get it to all the different processes. And that's the meaning of this all again. And essentially, this is just an example here with the MPI char and so on. But the overhead relies usually that broadcast itself has some overhead as a collective operation as any other collective operation. But if you just call once MPI all gather, you have just once this overhead. And this is basically better than calling multiple times, again, these collective operations. So using in general, of course, collective operations can also significantly reduce the overall runtime. As we were already knowing from one of our earlier lectures, you also don't want to do a send and receive and then do a for loop with all the processes. That would be a kind of equivalent beginner problem. Of course, for this, we have broadcast and the collective operation, which are much faster and much more efficient. So also when you think about the counterpart, all reduce, when we say, okay, we want to basically also put an operation to it, we want to do something with it, with the all reduce, then maybe a sum or so. Also, please use this. What we have found in some of the codes, like the one I was basically alluding to as an example, was then again a for loop, which then used again basically broadcast. And then the adding up was kind of implemented manually in another for loop. So in the end, you can basically also reduce there a lot of elements of the outer loop, so to speak, if you just use the all reduce, which does then parts of the MPI sum itself. Now, when we look further to optimizing now the MPI collective communication and the certain patterns I was basically explaining already throughout my discussion, essentially in this particular lecture, I said essentially Scalaska and other tools are able to here and there identify then also common problems in MPI applications. And here you have one common problem, let's say collective operations, right? And this is really an area where lots of difficulties could arise because collective operations always reflects that I have a whole team of MPI processes being affected. And by this, there's certain, let's say, waiting times or time spent in these communication calls where we maybe have to wait for others to complete their part of these operations. So again, this is a little bit a dry topic. You can imagine having this integrated in a cool tool, like for instance, Scalaska. Then you basically see that you can identify those automatically. You see that there's description around it. So that's why I do a little bit quicker here, the walkthrough of the matrix and of the idea of essentially what are now these different problems or patterns, because you see later on also video. And of course, it's not too much to exercise to look at each of them individually. You have usually the problem here of this fellow, which is a waiting time. So you see the MPI reduce where something should be reduced to. Right, the destination process here, root, is essentially a collective of many others that have to contribute to this reduce operation. And here it's essentially very early, right? That's why it's called early reduce, very early called in the program threads, because here you see all the different timelines. And essentially, this reduce is now much too early. So it's some kind of load imbalance again. And it's just waiting for the others to start this. While all the others are, let's say, pretty close to each other, that's fine. Here, this would be something what we could actually measure, because as you remember, we will measure now each of these different plots here, the entry time and their time when they go off. And this enables you directly to create a visualization like this. But also if you have a time-stamped these events, you can always identify those all which we basically involve here in this MPI reduce root operation, these others, when they are starting. And then with this, you can identify, of course, quickly the early reduce problem. But it's just, of course, just an example. So you can apply it to MPI gather and MPI gather V, but I will go now in all of these to all the different, let's say, details. Just I take the early scan as well, because firstly, you never have used MPI scan. You don't know what it is. And secondly, it's also a very powerful operation for, let's say, partial sums, at least. So let's look a little bit into that, which is a little bit, let's say, very similar to MPI reduce, but it does, of course, partial reductions to a specific amount of processes in the ranks. So when you think about what MPI scan is doing, just think about that you have this different rank identities here, right? 0, 1, 2, 3. And now important is that you start MPI scan and think about this index. So it will do, let's say, a reduction as an example, right? Partial reductions. If you do this only on those you specified with the index. And you see that a little bit here on this interesting graphic. You would have here rank 0, rank 1, 2, 3. If you call it on the rank 0, on the index 0, then of course it's just the A, right? So this is something which means it's just this rank. And there's basically no operator required for these values that you have here. Now, when you now come to essentially MPI scan and you basically say the index is 1, then you start with rank 0, have A, operator, and of course rank 1 involved, right? And reduce, or basically what you have here as a kind of operator. Could be also sum, a partial sum of just rank and 1, while all the others have, of course, also other values, but could be interesting. And then that's how it's continuous. So you say index is 2, you add to A operator E, you have operator E as well here on top of it. So, and the story continues. I think you know now the message, so it depends heavily on this E. And by depending so heavily on this index, you can imagine now that MPI scan and, calling them at different locations within your parallel program and at different certain times, while depending on each other, right? You see here, the sum, essentially, if you say a partial sum is needed here, we always have to wait. So these two, for instance, right? So this is a waiting time because MPI scan needs essentially this fellow. If you do it and execute it here, basically this one to basically be there. And the same is true for this and this. They are all involved in this and cannot continue basically. So they just wait. This one cannot continue until this sum is taken. So it has to start here. And essentially this part is depending on this rank. So it cannot start until this. So we have heavily waiting time again for 2 of these ranks. So this was a bit more in detail for the early scan problem. And you can now imagine you can do this with almost all MPI operations, right? In one way or another, it will be showing you some strange waiting times. Here's a late broadcast from, basically the root operator that's starting the broadcast. In the end, you can now go step by step through all of those and see how the problem lies by just checking the timestamps. And when I here do all reduce as an example, again, you can think about that similar measurements and similar late problems and waiting problems for basically these operations are also in all gather, are in basically all the different operations that we have in the collectives. The good news is you don't have to know them all by heart. That's why you see there are also no yellow blocks here to learn them all by heart. You have a tool that usually is, helping you in this sense. So it would not add to insight here if I go too detailed in this. You can imagine, of course, that this in a larger program anyway from HPC has to be done automatically, has to be done by doing the performance analysis tool. And the completion problems as well. Let's move ahead to a little bit other elements, which would be then the point-to-point communication. So you now leave the space of the collectives, but we will also see that particularly point-to-point communication can have also, let's say, different problems like a wrong order message or late receiver in the length sender. So here are two examples. Also here I go a bit more quicker. I think they're kind of self-explanatory by thinking about these are the problematic factors that essentially we wait unnecessarily for something in both the different ways of doing a proper send and receive, or as we have seen an asynchronous way of doing it, and then using the MPI wait. So it is basically applying in this sense then to the blocking communication and to the non-blocking communication, of course, also when you essentially combine them. Then the late sender problem are actually there in different situations, which is quite interesting. So you see also here, it depends again which MPI wait functions you really call, but essentially this all are in a way late senders of this MPI send while waiting for the receive a long time in the MPI wait all, where this time here, which we see could be probably much better used, but is something which needs to be then, of course, restructured in the parallel application. Another type of late sender here, where it's a little bit about the different sources, locations, and different, let's say, wait clauses, also not so important to know by heart. It's just basically done in the wrong order. And you can continue. And the good news is now, you don't have to do this all and know that by heart. You see here, when you then open Scalaska on the trace that you have done, so you basically do a Scalaska skin. With this, you have the instrumented code, you run the code, and you trace it. And once the trace is available, you can have now the Scalaska and do replays and look at the performance and see where your problems are. And here, you see essentially most of the time is in the execution space here. Here are the different elements, and you will look at the overhead is quite okay. And here's a late sender as an example where you can look in and see where's maybe the time spent mostly here. It is actually then in the MPI wait all and what basically processes are really affected. So this over time then again and again is giving you then ideas of really automatically analyzing and going step by step where could be potential problems. Maybe sometimes you cannot really correct it because it's just too complex for an application to change. Maybe the physics at that point in time in your application are too complex to really bother. So you really swallow this waiting time maybe. But good chances are you can increase your waiting time, especially if it's significant. Here's another example that you basically have a late receiver, right? So not a late sender. Now we are talking about a late receiver. Still, the concept is just the other way around. You have a send. It is, of course, here waiting properly to finish the operation and cannot continue. So it waits until the MPI receive is really done with the job. And the same is when doing it with the non-blocking communication and combining it with the MPI wait. Good, so much for the communication, but what we also learned in earlier lectures in MPI was the synchronization on collectives. So we said there's a waiting required and also barriers. So just quickly that, of course, also in the synchronization primitives, you have essentially this waiting time. The MPI barrier, for instance, is very known because basically the caller basically is so much blocked until all processes in the communicator have been actually called for it. So it's really a big synchronization statement, and you can imagine when some ranks are really early finished, they have to wait a long time in the barrier. And if there are many different, let's say, waiting times like you see here, and just one is really, let's say, not waiting much, then there's maybe also cause for trouble. And similar, of course, the other way around with the completion could be also similar. So OpenMP, of course, is different then at that point in time when you think about also there is synchronization a problem. But of course, also this can be detected in a very similar fashion when you think about the timestamps. Again, this could be also an OpenMP barrier where you have to wait and has lots of wait times here in order to identify this specific pattern Now, a problem also, as you know from OpenMP, is then this critical regions that we discussed in OpenMP, where you need to really lock certain elements. The lock means then you have to acquire locks and release locks. And here it could be also that when you want to acquire a lock, but it's already locked, of course, by some other processor, you have to wait a long time. It's just naturally to do so, but it in fact impacts, of course, your parallel execution behavior. So maybe you want to release the lock earlier here so that you can reduce this time or whatever it is to do in order so that the processor here or the thread at that point actually is not waiting so long. But of course, critical sections are needed, but they of course hamper your performance significantly. Now, towards the end, essentially, before we come maybe to a video on really Scalaska, and it shows you a little bit more in life how that all works. Here's some implications, of course, on the optimization on hardware and I/O. You can imagine parallel I/O patterns matter a lot. Parallel I/O formats that we discussed have a huge impact in your basically reading, and with this basically also a big impact in your execution time. Examples include that, you know, mostly we use binary file formats all the time. And the reason is that they are also written directly, basically as binary file formats from the application and read as binary, because the computer anyway has to transform them to binary formats. But if you want to put everything in a readable fashion, let's say human readable fashion with numbers, with arrays, and drop it to disk, you will have performance implications. You make it nice and it looks readable and it's very perfect. But then on the other hand, you basically don't have it binary anymore and you lose a lot of performance. On the other hand, you have seen with HDF5, for instance, a binary file format, you can have viewers looking at this, right? We were investigating some of the Mpi Scan HDF5 format, which was a parallel file format binary. So you cannot just more it basically on your Unix. You cannot just look inside it, but we had a HDF5 view where we can actually look, investigate still the binary file format. So nothing is lost by using binary file formats. On the contrary, for basically optimization on hardware and I/O, particularly I/O, it's really parallel I/O helpful. This has to do, of course, a bit also with your network topologies. Are there I/O nodes? Are there, let's say, is there the, if you then want to gather all the different, let's say, elements from all the different processes, of course, it has network impacts, right? If they share bandwidth, as we had also earlier in one of the lectures, this is an important part as well, where we have to think about how well are actually now these different nodes and so on interconnected. Right, so in a way, that's really the main messages I wanted to give. Of course, you know, it's a really big topic. You can have really a whole week just doing nothing else than debugging, profiling, and performance optimization. It's a long process. Here's now a video that also shows you nicely that within Scalaska, you can not only, let's say, have this performance properties identified and so on, you also see directly their description. You can learn something about your parallel performance behavior of your application. That's why I think, although it's a bit long with 5 minutes, but it's really worth to look into this video, what we will do right now.
If you have wondered where your hybrid MPI and OpenMP application is spending its time, what resources it's consuming, and where its performance bottlenecks lie, then our tutorial on practical hybrid parallel application performance engineering may be useful for you. In this tutorial, we will present live demonstration of HPC performance evaluation tools that include ScoreP, the instrumentation toolkit that allows you to generate profile and trace data files. We use Scalaska to analyze these trace files and search for patterns of inefficient behavior and generate performance properties that can be stored in call path profiles. These call path profiles are then analyzed with Tau's Paraprof profile browser or the Cube profile browser. We also feature interactive trace visualization with Hampier in this tutorial. To give you an example of these tools, here is the Cube Profile browser, where in the first pane, we see what kind of performance metric was collected. This shows you data from Scorpy and Scalaska, where we see metrics such as time, the number of visits, and performance properties such as weight at barrier, late in receiver. The late receiver bottleneck is a performance property that occurs when a send operation is blocked until the corresponding receive operation is called on the other process. And this pattern refers to the time spent waiting as a result of this situation. This is the time the process could be doing some useful work. And to see where this occurs in the source code, you can look at the call tree and follow the call path. It shows you the location of the bottleneck, and we can see in the third pane the system tree where it occurs on the machine. So you can expand a particular node and see which rank was involved with this performance property. We can also see the box plot and the system tree. Other tools such as Paraprof can show you the profile files. Here I am looking at a profile output. Let me unstack the bars and click on a color which represents a function. Here's the name of the function, and we can see how it performs on all the MPI ranks. If I click on the MPI barrier, I can see how much time was spent in MPI barrier. This is the 3D visualization provided by Paraprof, where I can see the MPI ranks along one dimension. I can see the names of functions along the other, and the height metric can represent the time spent in the function exclusively. I also have panes that allow me to crosshairs, which allow me to see which function is involved. Here I see a bar plot, and I can zoom in to a given location and see the thread that is involved. Here I can see that the loop in this function on rank 199 took 129 seconds. I can see the shape of the profile in 3 dimensions. This is the Paraprof profile browser. We will also demonstrate the Vampire trace visualizer, which shows you exactly what each rank and thread were doing along a timeline. So we can zoom in to a given segment of a timeline and see what was going on in the application. So we see a wait and an MPI Iceland operation over here. Here's another example where I can zoom into a section of the timeline and see exactly what each thread, each OpenMP thread was doing. If you are wondering how we instrument the codes, there are various ways to do that. Here is an example. I can build an application, say the NAS parallel benchmark, and instead of running it in the virtual machine like this, I can simply add now exec-d score p. And when this executes, I'll generate performance data. And analyze it in Paraprof or Cube. So I can see exactly how much time was, say, spent in MPI receive on rank 0, which is 2.4 seconds, or launch Vampire directly on the trace files. Thank you.
All right, so you have seen basically how Scalaska works, and you also on top got a little bit an idea how Vampire, how also ScoreP is actually working on in context. So of course, just small demonstrations here, but these are all very powerful tools that are really very good if you want to scale up your HPC application. So that's all for the lecture today. The next lecture will be about the GPUs and accelerators and new developments in that area. So thank you very much and see you next time.